Suppose you have two statements like P and Q. The conditional of Q by P, which is written as if P, then Q, or P implies Q, and is denoted by P, then Q, is basically a conditional statement. It is false when P is true and Q is false. This is the only time that this statement is false. We also call P the hypothesis and the Q conclusion. Let's take a look at the truth table here. The truth table for P then Q is written this way. First of all, you have P, you have Q, you have P then Q. Since you have two statements, we expect to have four combinations. 2 to the power 2 gives you 4 combinations. P can be true, Q can be true. True then true is true. P can be true, Q can be false. True then false is always false. P can be false, Q can be true. False then true is always true. And both of them can be false. False then false is a true statement. We want to show that P or Q then R is equivalent to P then R and P then Q then R. So in that case, if you have a statement like this, a composition of two statements, you can replace it by the statement on the left-hand side. Or if you have a statement like that on the left-hand side, you can always write it in expanded form this way. So let us begin. We're going to form our truth table. In using our truth table, we have 1, 2, 3 statements. 2 to the power 3, you get 8 combinations. So we expect to have 8 combination of P, Q, and R. Let us list these statements. P, Q, R, P or Q, which is this statement here. P then R, which is this statement here. The order is not important, everyone. You can just rearrange this as you see fit. Then Q then R. On the left-hand side, you have this compound statement. So P or Q then R. And finally, on the right-hand side, you have the statement, which is written on the right-hand side. So let us begin. P can be true, Q can be true, R can be true. True or true is true. True then true is true. True then true is also true. And then since P or Q is true, R is true, true then true is true. This is your value for the left-hand side if all of these statements are true. The value on the right-hand side is also true and true, which is true. So far, these two values are the same. We have 7 more rows to check. True, true, false. This is another combination. True or true is true. True, then false is false. True, then false is also false. P or Q, then R. P or Q is true. R is false. True, then false is false. So this is your value on the left-hand side. The value on the right-hand side is the combination of these two using and false is false. So these two rows are also having the same truth values. The next combination is P is true, Q is false, R is true. True or false is true. True, then true is true. False, then true is also true. True, then true is true. This is your value on the left-hand side, and the value on the right-hand side is the combination of these two using and true is true. So these two are also the same. You can continue this process and check in the rest of the combinations. You're going to have the exact same values for these two statements. And you see you have false and false. So here you have 4 rows. We need more 4 rows as well. So false, true, true. False or true is true. False, then true is true. True, then true is true. And then here you have P or Q, then R, true, then true is true, and true is also true. Very good. As you can see, this process is time consuming. You can always use the equivalence theorem and the laws that we learned in previous lesson and apply those and show that left-hand side and right-hand side can be simplified into two equivalent statements. We have one more rows or one more combination, which is showing that all of them are false. By checking each of these combinations, we just showed that the left-hand side and right-hand side values are exactly the same. So what is our conclusion? Our conclusion is that these two compound statements are logically equivalent to each other. Very well. A common question is, how do we find the negation of implication? Can I just distribute the negation over parentheses here? Is it going to be not P, then not Q? It's not. So to find the negation of implication, we have to work with the equivalent statement first. We can obtain this result by using the following equivalent relation between P then Q and not P or Q. Then you can apply De Morgan's law, which says that, hey, the negation of P then Q can be written as the negation of not P or Q, which is the same as P then Q. And then you can distribute this negation over or using De Morgan's laws. And then here you have not P and not Q. Not P is the same as P. So you have P and not Q, which is the exact same expression that you see on the right-hand side. If I ask you to find the negation of any statement, including implication, first you have to rewrite the implication in this format, then apply De Morgan's laws. When it comes to implication, we have other definitions as well. One of them is contrapositive. Contrapositive of a conditional statement is if not Q, then not P. Contrapositive is equivalent to conditional statement. The contrapositive of P then Q is not Q, then not P. You can also define the converse and also the inverse. The converse of P then Q is Q then P, and the inverse of P then Q is not P, then not Q. Again, what is important? The contrapositive is important. We use this especially when we try to prove some statements, some theorems, some lemma. Suppose P is a square, then P is a rectangle. This is your statement. You have the hypothesis and you have the conclusion. The contrapositive of the statement is if P is not a rectangle, then P is not a square. We don't care if these statements are true or false. We're just practicing to writing the contrapositive, converse, and inverse of these statements. The converse can be written as if P is a rectangle, then P is a square. So we just switch these two. Now the inverse is if P is not a square, then P is not a rectangle. Another example for you. If the decimal expansion of R is terminating, then R is a rational number. Well, the contrapositive is if R is not a rational number, then the decimal expression or the decimal expansion of R is not terminating. The converse is if R is rational, then the decimal expansion of R is terminating. And finally, the inverse can be written as if the decimal expansion of R is not terminating, then R is not rational. One last example for you. If n is prime, then n is odd or n is 2. Again, guys, we don't care if these statements are true or false. It's just pure practice. The contrapositive is if n is not odd and n is not 2, then n is not prime. Please be careful about the and or, how we change these using the negation. The converse is if n is odd or n is 2, then n is prime. The inverse is if n is not prime, then n is not odd and n is not 2. So 3 examples for you to feel a little bit more comfortable about the definition of contrapositive, inverse, and converse. And again, the contrapositive and the original statement, they are always equivalent to each other. That's the takeaway from writing the contrapositive of a statement. The statement and the contrapositive are always logically equivalent to each other.